Yeah,
Oh, um, wait, am I recording the right screen? I hope so. Yeah. Go
yeah,
ahead.
you see my screen now.
Yeah, I see your screen.
Yeah, thank you. So, hi everyone, I'm Trang Nguyen. Today, I would like to introduce to you my previous causality pressures with Rainbow and with my team for my master degree. So basically, I have three past projects about causality in physics, in multimodal data, and in biology. And I will share a little bit about my next direction about causality. So the first one, published at NURI, reusable slot-wise mechanism that work with Rainbow and Yushu. The original task is video prediction that we are given a few initial frame with some object and initial movement. In this case, it's a gravity free falling and collision. So we try to capture the causal relation of physics rule among object and the static object. In this case, the blue and the red ball will collide to each other and collide to the static object like the glass and the blue ground. And some traditional approaches to solve the task, like they input the home frame and predict the next home frames. So that's not good to capture the causal relation among the objects. And some modern approaches, they try to decompose the original input into slots. Slot is a representation in the latent space. It could be decoded into object or background, like like this one. In this case, we have slots capture object and a part of object of the class. And they also try to decompose the original object dynamics into basic movement, like just to move horizontally, move up and down, or just to handle object collision. But the problem with the previous tasks is that they have some inductive biases on object communication density. It, they define the density of communication to be too dense or too sparse. So it's not good for generalization to unseen cases. So in my work, I proposed a new communication protocol among object slot and mechanism that I proposed the CCI, the Central Contextual Information, that played at a communication bottleneck among object and mechanism. Like the CCI will receive the input at its own slot at one times and capture the current context of the system and use it to map the object slot to appropriate mechanism. And the CCI have object to be able to see the update of other slots in real time. That means when we predict the red object, the in the turn of the yellow object will see the update of the red object. Yeah, that could have to enhance the causal influence among objects. And then with one slot and one mechanism, we have one object slot, yeah, at the next time step, and then combine it together to have the output frame. Yeah. Let's see a little bit about of the part of result. We did an experiment on 5 datasets, but for simplicity, I only saw one of them. So here is the uh, fire dataset that I saw earlier, and the full of five of a slot we have. And in this environment, we define five mechanism is randomly initialized. And during training, we expect that the model will decide the role for its mechanism. And let's say after training, its mechanism can do with the task to the object. Like in the first step, we receive the input uh, and static object. We could see that from step one to step two, the two balls will collide to each other and change the movement direction. And to handle the collision, mechanism 2 is activated on the blue and the red object, as you can see here. That means the CCI choose mechanism 2 to apply on the blue and the red object to handle the collision. And with other objects, like a part of the glass, they just stay, uh, just remain the stated from the previous step. So they apply the mechanism 4. And if step 3 to 4 and to 5, the two balls just falling down. So like the red object falling down. The instead to falling down, so we apply mechanism 5 for falling down movement. So that means uh, although we just randomly initialize mechanisms, but after training, the CCI can define can assign the specific role for each mechanism. So that is the first project. Do you have any question for the first project? No. So I move into the second project. This one is published at EMNLP 23 with my Japanese supervisor for master course. The original task is the VQA task that we received input image and questions. And the problem with this task is that human has some kinds of biases that sometimes not only rely on the correlation among object among question and the answer, like uh, question start with is this usually supposed to be a yes no question instead of a multiple choice, or there's some correlation in the dataset, like for question how many in the dataset that capture the real data. Mm, we collect the answer for, like, when we ask how many, we will answer the number 4, 5, and 1, for example, and we plot the distribution of answer for the whole trend set. We could see the answer 2 is dominated. But in this case, in the test set, we do not have answer 2 anymore, but answer 1 and 0 are dominated. And we need to overcome this correlation by enhancing causal relation among the entity in the question and image. So my hypothesis is that if we only consider a monolithic strategy, we are that we will use a single model to encode the image in question, then use a single model to generate the answer. It will not good to capture the causal relation among them. So I try to create diverse strategy across the input interpreting and answer generating stages. And I proposed cognitive pathway VQA. The cognitive here is like at each stages of input interpreting and answer generating, I will I will choose among multiple choices. Like it inspired from human brain that in front of a problem we need to consider to choose the best option. And I designed two kinds of model that cognitive inspired model, like a simple MOE that have a gating model and a set of expert model, just like MLP model. And another type of model is just a single MLP model that's represent for the monolithic strategy. Uh, and then I generate four different answers with different flow, like the full reasoning flows is handled by the cognitive model in both of interpreting and answering stages. And if we only use one cognitive model and one monolithic model, we have the monolithic flow. And if we only use input question to generate the answer, we have a unimodal flow. And to have the final answer, I take the subtraction of the overall answer. The overall answer is the sum of answer probability from four strategies. and subtract it to the biased answer. That's from monolithic flow and unimodal flows to have the final answer that will enhance the causal reasoning among input interpreting and answer generating. And these subtractions come from the causal equation called uh, come from counterfactual learning. That is a total indirect effect equal to total effect subtract to natural indirect effect. Yeah, yeah. Because this one is just an overview of my method, so I will not go deep into the technical detail. Yeah, and let's see the results. We have the imbalance data sets at the beginning, and CopPQA is our method that can generate the answer distribution that's close to the test set compared to the baseline DBQA. They still rely on some biased answer, and the same for the baseline CFBQA that they strongly rely on the biased answer with the answer 2 and look deeper into the answer consideration. For a question, is it a real dog or a toy dog? CopPQA, our method, can answer the correct answer. And also, they consider a relevant answer with a stuffed animal compared to the baseline CFPQA and DVQA. They trap on the uh, bias that it is questions that with it is usually supposed to be a yes no question and answer yes and no. And we also experiment on the medical data sets. Yeah, and in this case, we have a correct answer compared to the baseline MMQ. And in the third project,
Sorry,
uh,
Chen, can I ask a question about our second
yeah,
project?
sure.
So if you go back to the method,
Yeah,
okay. So your each this green box is a MLP, right?
yeah, right, right.
And your when you say full reasoning flow, it's a kind of you are disentangle different step in your reasoning, so it break into different steps, right?
Yeah, that's right.
The monolithic flow means you skip some intermediate step while go more directly to answer.
Yeah, the monolithic flow that use the MOE in input interpreting and it generate an interpretation of the multi-model input. But then they only use a monolithic model to generate the answer.
Okay, I see. Then the unimodal flow is go you jump directly from the input to output. Am I right?
uh, unimodal flow, that means they only use the input questions because in the task, the bias in the answer is very strong. That the model tends to only see at the questions and answer and overlook the image. So I
Oh, I
want to
see.
capture, yeah,
I see.
capture the bias in question.
Okay. Okay, I get it. So that let me see. So it means if you break down your flow of thinking into more compositional step, you will get better generalization across different setting. Am I right?
Yeah, yeah, and we need to subtract the overall answer, the total effect to the indirect effect. Yeah, that is the main idea.
I think this agree with recent last year's a large language model paper where they realized the large language model do those kind of reasoning by estimating what you call here as a monolithic flow or unimodal flow. Uh,
Yeah.
Jump the chain of reasoning while use a f function learned by the model to estimate every single step in between.
Mm.
I got one question. What does this MOE did here?
We in a hard selection, mixture of expert.
But why is this a mixture of expert related to your full reasoning flow?
Yeah. One state that involve reasoning process. That means they must choose the appropriate experts to
Oh, I
to
see.
present the input. Yeah.
I see.
Yeah.
Okay, so the choice of expert is regarded as the reasoning process in your setting. And you
That's
are using Rumble softmax or
yeah. I use the gumbo submax, gumbo, a hard gumbo submax.
Yeah, the
Gumbo
name is
Max.
completely correct. Gumbo through hard max. I think that is what it should be called. Yeah. Okay.
Yeah,
Get it. Okay. Yeah. That's great. Thank you.
yeah, thank you. And in the last project with Demo and Joshua published at workshop, generative AI and biology workshop. Yeah, the original task is to predict the velocities of gene in the gene regulatory network given the gene expression level. And the challenge of this task is when we work with real human gene, we have the high level of uncertainty that lead to multiple possible causal structure among genes, and also the large scale challenge. And based on the previous task, based on the previous setup and baseline, that we break the original task into like the first step is to predict gene structure, and then and we try to predict the very possible structure because yeah uncertainty involved in the environment, and based on that structures we predict the velocity, and because we try to predict the very possible structure that match to the objective of GeForce, the generative uh, flow network. Yeah, that's I think some of you are trying to jump into this method. Yeah, and you GeForce at the backbone of this work. And our baseline dynamic GeForce, they 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 predict the structure and velocity that independently among genes, which is not good for the causal discovery task and also not correct in biology theory. So I propose a swift dynamic shift on it to first solve the problem of the river task about independently prediction among genes, and also try to speed up the prediction process. And I introduced two novelty here. The first one is to encourage gene wide influence that in one prediction process, I try to let the past prediction influence the current step prediction. Like if we are given five gene with the number from 1 to 5 here, in the first day, if we start with gene 1, at step 1, I will predict all incoming edges that influence gene 1, and also predict what to predict next in the next turn, that is gene 3. And then in the turn of prediction of gene 3, I will acknowledge the prediction that were made on gene 1 and follow that concept to to the final gene. Yeah, that means we when we have only common edges to all genes. That's the first novelty, and the second novelty is that we encourage the parallelization in prediction. That means different from the previous baseline that predict only only one edge incoming to one gene at a time. We predict all edges uh, based on one forward probability. We sample all edges. Yeah, that can speed up the prediction significantly. And we use the detail balance alternate objective for those who working on GFNS can refer to. Yeah, and this work is still in process and target to rip this year or clear. So if you want to join, I'm very happy to involve you to the project. Yeah, a little bit about the results here. We have about the accuracy in predict causal structure. We have a swift dynamic shift net really fine tune for the best performance. We outperform baseline in the large margin and also have uh, less parameter and faster training time. And when we evaluate on the scalability, we have when we increase the number of variables to 20, 50, and 100, we could see with 100K, we have significantly less training time and number of parameters, but also have a slightly higher or outperform baseline. And this is the first project. Do you have any question? Yeah, if not, so I would like to introduce my next causality research. My very long-term goal is to enhance the healthcare system with increasing of health equity. And based on my past research about causal AI, I want to improve causal AI for medicine, including clinical and biomedical medicine. Yeah, that's all about my presentation. Do you have any question?
Any question, feedback, comments on Chan's talk or her research experiences? Well, if no, I would like to thank Chan for her nice talk, and thank you so much for attending the meeting. We can end earlier today.
Yeah, thank you.
Thank you. Bye bye.
Thank you. See you.